thank you very much. So I have to say that it's really a pleasure for me to be here, and it's quite moving also. I mean, I attended 2 summer schools here in Grenoble. This is my second one. So the first one was in 2007. And yeah, so at that time I was basically studying what I'm going to, to talk about in this lecture. So it's, yeah. Okay, so thank you very much. And one more thing I really have to say, I apologize in advance, but I promised that to my daughter. So I'm going to use for the first few minutes her personal notes about hyperbolicity. So, okay, so I'm filmed, so she will check, right? So I have to. Okay, so so the goal of this 4 lecture is to first of all to explain very, very basic and introductory stuff about Kobayashi hyperbolicity of complex manifolds. Then I'll try to explain this construction of this algebraic differential equation that you can define on complex manifolds as a tool to study hyperbolicity properties of manifolds. These are so-called Green-Griffiths jet differentials or Desmailly sample jet differentials in the invariant version. And then the third and the fourth lecture will be about some interaction with foliation theory. And so the third lecture will be about some example showing that it's more or less not possible to characterize algebraically the locus where holomorphic map from the complex plane to manifolds, where there is the holomorphic map, the image of holomorphic maps from the plane to the complex manifolds. And then the last lecture, I'll try to give a rough idea of this celebrated McQuillan theorem about the Green-Griffiths conjecture for surfaces with positive second Segre number. So it's maybe too ambitious. I don't know what I really going to do, but we'll see. Okay. Okay. So today it will be very, very basic. So I apologize with experts and so on. But after all, it's a school. So let X be a complex manifold or space. Okay, so everything I'm going to say works very well for complex spaces, which is something which is locally isomorphic to some analytic set in an open set of Cn. Okay, but we can think just at complex manifold. It's fine. And okay, I changed maybe. Okay, so the first goal is to define an intrinsic distance on X. Okay, so here are pseudo distance because in general it would be not a distance. And by intrinsic, I mean something which is connected with the complex structure of X, right? So in particular, I mean invariant under biolomorphism. Okay, so I want to make X into a metric space and or pseudometric space, and I want that the group of automorphism of biolomorphic automorphism of X to be contained in the isometry group for this distance. Okay, that's the goal. Okay, so the model for this is the Poincaré disk. Okay, so by this I mean delta is just the set of complex number of modulus less than 1. Okay, and on this disk I can define a metric. I mean, a Riemannian metric in the sense of a Hermitian metric in the sense of differential geometry, which is the Poincaré metric, which is defined as follow. Okay, so I put this 4 here. So often you don't find this in literature. Often you find it. Okay, it depends if you want this disk to be with constant curvature equal to -1 or -4. Okay, yeah. No. No. That's the only thing in which I'm expert in mathematics, where to put I in this. Okay, that's the Hermitian metric, not the Kähler form. Okay, and thank you. Out of this, you can look at this Kähler form, omega delta, which is 2I okay, so that's the Kähler, the fundamental 1-1 form associated to this metric. So if you have 4 here, you have 2 here. Okay, so let me. Otherwise, you have nothing here. You have 1/2 here. Okay. Okay. So that's the Poincaré metric and the Poincaré Kähler form. Okay. And now you want to compute the Gaussian curvature of this metric on the plane on the disk. Okay. And so how do you compute the curvature? So in this case, there is a very, very simple formula. You just take this guy here, okay, call it lambda, for instance, okay, and the lambda of z. So the Gaussian curvature at the point z is just 1/lambda times the second derivative of the logarithm of lambda. Okay? So you have just to do computation, and you find this guy here. And so if you make your computations here, you will find that it's constantly equal to -1. Okay? That's why we put a 4 here. Okay. So out of this infinitesimal datum, of course, you can cook up a metric space, okay? And you just define the distance between 2 points by taking all piecewise C1 curve connecting these 2 points, and then you integrate the length of this curve, and you take the infimum, okay? And out of this, you get this Kobayashi, this Poincaré distance on the disk. So you take 2 points. I just give you the formula, even if it's more or less useless, but why not? It can really be computed, and it's a logarithm of these terms, like here. Which I discovered 2 days ago to be 2 times the inverse of the hyperbolic tangent of A minus B bar. Okay? If you want, you can take this as a definition of this function if you don't remember. Yeah. Okay. Good. Okay, so why is this stuff important? But from the point of view of complex analysis, you have this fundamental Schwarz-Pick lemma, okay, which I'm going to state now. Which tells you that if you have, it's a generalization of the classical Schwarz lemma from a function from the disk to the disk, fixing the origin. So you have no matter which holomorphic function from the disk to the disk, holomorphic. And then you do have that the following inequality is true for all z in the disk. And you have equality if and only if the map is an automorphism of the disk. Okay? So if you look at this equality and you look at the expression of this infinitesimal metric, you will recognize that that's just telling you that infinitesimally the distance is going to decrease. Okay? So this you can translate by ds square delta greater than or equal to f star of d square delta. Okay? You just substitute here and you find this thing. Okay? Okay, so of course this means that if you integrate this relation, you have the same property for this integrated distance. Okay, so holomorphic map from the disk to the disk decreases the Poincaré distance. Okay, and as I was saying here, by looking at the inverse, if it exists, you see that bilomorphic automorphisms are isometries for this distance. Okay. Okay, so now I have this model on the disk.
Sorry, what's Kähler?
Sorry. That holomorphic.
Okay.
Holomorphic.
You say that there is equality for every point or just in
Just one point.
Just 1 point.
Yeah. Yeah. Okay, so now we want to translate this notion to complex manifolds. Okay, so in some sense we want to use this thing on the disk to build a distance on complex manifolds. Okay, so there was a first attempt which is quite fruitful by Kähler, who was looking to map at maps, holomorphic maps from a complex manifold to the disk. Okay, this works very well and permits you to define a distance, but it's, I mean, if, for instance, if the manifold is compact, you don't have such maps. I mean, non-constant. Okay, and so a colleague of mine and the chairman of the session told me that he was asking to Kobayashi himself why he introduced this new distance, and Kobayashi apparently answered something like, nothing, I just was looking at the Kähler distance and I want to take the dual point of view, right? Okay, so let's take the dual point of view of something we didn't do. Okay, so want to define some pseudo distance on X. So by pseudo distance, I just mean something which has all the properties of actual distances, except perhaps separation of points. You may have two distinct points which are at distance 0 a priori. Okay, that's a pseudo distance. Okay, so now take P and Q, point in X. Okay. And I define for you an object which is called a chain of holomorphic disks connecting P to Q. Okay? So, a chain of holomorphic disks connecting P to Q is, so it's the following data. 1, points P0 equal to P, P1 up to Pk equal to Q in X. 2, pair of points A1, B1, AK, Bk in the holomorphic in the unit disk. And 3, holomorphic maps F1, Fk from delta to x such that Fi of Ai it's equal to Pi and Fi of Pi minus 1 and Fi of Bi equal to Pi. Okay, so that's a chain of holomorphic disks. So what am I doing? So you have your manifold X, you have 2 points here. Okay, and you're taking this is P0, P1, P2, P3, P4. Okay, and you take some image of holomorphic image from the disk, and you choose 3 images of these 2 points in the corresponding disks. Okay, and then once you have such a chain that you call alpha, for instance, so alpha is such a chain, and you call the length of alpha is by definition, so you use these points that you have chosen on the disk, okay, this pair of points A1, B1, etc. And you measure the distance using the Poincaré distance on the disk. Okay, so it's defined to be rho delta of A1, B1 plus rho delta of A, K, BK. Okay, so that's the length of my chain alpha. And then I define the distance between P and Q to be the infimum of the length of alpha when alpha varies among all these chain connecting P to Q. Okay? That's a definition. Okay. Good? So some properties. So first of all, dx is a pseudo distance. Good to know. 2, it is continuous as a function. It's continuous. I mean with respect to the Euclidean topology in X. Okay. 3, so if you have this some holomorphic map from one manifold to another, then it is distance decreasing as wanted. 4, if you make the same construction on the disk, you recover the Poincaré distance itself. And 5, and this boils down from property 3, the automorphism group of X, I mean biholomorphic automorphism group of X, is contained in the isometry for this pseudo distance. Okay, so actually automorphism are isometries. Okay, so these properties are all simple to prove. Okay, there is nothing hidden. Okay. Okay. So it seems that we went the other way around, right? So for the Poincaré disk, we defined first the infinitesimal version, then we integrated it, and now we are defining first the distance. Okay, but there is an infinitesimal version too, which I'm going to tell you at once. So you pick a vector, a tangent vector, and you want to measure its length, okay, in some sense. So you take some vector, some tangent vector at some point x0 in x, okay? And let me call, following Kobayashi's notation, fx the length of this vector. And it's given. So it's really the infinitesimal version of what I'm saying, okay? So I want to use the Poincaré infinitesimal distance on the disk, okay? And so this is the infimum of the length of tangent vector u with respect to the Poincaré distance on the disk, such that u is a vector, is a tangent vector to the disk, and you have some holomorphic map from the disk to x, such that if you take the differential of f and then you push forward u, this vector using this differential, then you drop on v. Okay? Okay. So this can be seen to be the same thing, since the automorphism group of the disks is isometries and also acts transitively on the disk. Okay, you can also rephrase this in the following way: you take the infimum of the number of the positive real number of the form 2 lambda. I'm sorry for this 2, but it's because I wanted the disk to have -1 curvature. So, okay. Such that there exists some holomorphic map from the disk to x, which sends 0 to x0, and such that lambda f prime of 0 is equal to v. Okay? So f prime of 0 is just a notation to say that you take the differential of f at 0, and then you send this vector, okay, to x. Yeah. In the first definition, not necessarily, but that's what I was saying. Since you can move everything by automorphism of the disk, you can send back everything to the origin, and it's the same. Okay. By precomposing. Okay. Yeah.
Do these 5 properties characterize the Kobayashi metric, or is there another metric with this nice property?
It's the biggest with this property, Kobayashi metric, in some sense. It's the biggest invariant, it's the biggest pseudometric, such that it has this property when you look from maps from the disk. Okay, you can characterize this like this. Yeah. Okay. Okay, and then let me add here, yeah, that these two definition matches, and you have this theorem by Royden, which tells you that indeed the distance, the Kobayashi distance between P and Q is actually the infimum when you look at piecewise C1 curves of the integral of fx along gamma. Okay, so fx of, say, gamma prime. Okay? So this fx is less regular than dx. It's just, so if you look at it as a function from the total space of x to R, it is upper semi-continuous only. Okay? Okay. Let's see an example. Hey. Alors. So these notions have been introduced by Kobayashi in the early 70s. Okay, so. So this subject was a really fertile subject. It's quite amazing. If you look, the very first book Kobayashi wrote about this stuff in the early 70s, it's like a 100-page book. Very small, very nice. And then Kobayashi made a second version in the mid-90s, and it's like 500 pages, okay? So it's really growing up a lot. Okay, so examples. So first trivial examples. So take X to be Cn or Pn. Then you have that this intrinsic to the distance is indeed identically 0. Okay, and also the infinitesimal one. Okay, so why is this true? So basically, it's because in C, for each point and each tangent vector, okay, there is one straight line, okay, a fine complex line passing through that point with this tangent, okay, and so you can embed holomorphic disks by taking just the image of bigger and bigger disks centered at 0 on that line, okay, with a good direction, so that this lambda indeed goes to 0, right, because of rescaling. This infinitesimally, and from the integrated point of view, you take P and Q in Cn, and then you just take this sequence. You take this chain of holomorphic disks. So each chain is made up just one disk. Okay, and it goes from delta to Cn, and you map Z to P plus NT. You map NZ Q minus P. Okay, maybe N has to start from 2 or something like this. Okay, and so you see that Fn of 0 is equal to P, and Fn of 1 over N is equal to Q. Okay, so these 0 and 1 over N are your A1 and B1. Okay, and so they get closer and closer, and so this point are at 0 distance. Okay. So once you have done for Cn by continuity, okay, for Pn it's the same. Okay, you have to be a little bit careful. Yeah. Sorry. Yeah. I wanted to say that it's enough to use that it's continuous, but it's not the same distance. Yeah, so yeah, a priori. Yeah. Okay, so more generally, if you have some holomorphic map, non-constant, from C to X, so from now on, I call this thing an entire curve. Holomorphic non-constant image of the complex plane. Then the Kobayashi distance of P and Q in X is equal to 0 if P and Q are in the closure, not the risky Euclidean closure, of the image of C. Okay? This is because of that property number 3, right? Plus the fact that on C the distance is identically 0. Okay? And the closure is by continuity of the distance. Okay? And also Fx of V is equal to 0 if V is some vector in the image of the differential of f. Okay? Okay. So these are basic examples of something where you should keep in mind that this thing with a lot of complex line inside, or more generally non-constant holomorphic images of C, are have zero Kobayashi distance in some sense. Okay? So, so now let me define for you what hyperbolic manifold is. So if X is a distance, so if you have, moreover, separation of points, okay? Yeah, because X is a manifold, right? Yeah. Thank you. Okay, and also X is infinitesimally hyperbolic. Kobayashi hyperbolic. If fx is positive definite, and moreover, since you want some uniformity also in the non-compact case, okay, so you ask that fx of v can be bounded from below by some epsilon time the norm of v with respect to some fixed background emission metric, omega, when when v is in Txx and x is in some compact set of x. Okay? So that's the definition of hyperbolicity. So it's really, so from now on I will call a Kobayashi hyperbolic manifold just an hyperbolic manifold, but please keep in mind that it's not the usual, it's really not the usual notion of hyperbolic manifold restricted to complex manifolds. Okay? So the usual notion of hyperbolicity in Riemannian geometry, it's a complete Riemannian manifold of constant curvature equal to minus one. So in particular, it's universal cover, it's isometric to the ball with a Poincare metric, and it's not always the case in here. Okay? But they share some property. In particular, we will see how these notions are connected with the negativity of curvature of manifolds. Okay? We'll see in a minute. Okay. So let me tell you some properties. And then I'll do some examples. Okay? Some non-trivial examples. So first of all, if X is hyperbolic, then if you take any submanifold or subvariety of X, is hyperbolic too. Okay? That's again the decreasing property. Okay? You just look at the inclusion map, which is holomorphic, and okay? Then you have that, for instance, a product is hyperbolic if and only if x and y are. Two factor must be hyperbolic. Okay? Then it behaves nicely with respect to topological covers, étale covers. Okay? So if we have an étale cover, say topological cover, then X is hyperbolic if and only if x tilde is finite or not finite cover, of course. Okay? Then you have that, of course, as I was saying, if you have an entire curve in x, then x is not hyperbolic. Always because of the decreasing property of distances, plus the fact that C is not hyperbolic. Okay? And last thing I wanted to say is that if x is hyperbolic, then the automorphism group of x is a real Lie group. Okay, whose Lie algebra is given by complete holomorphic vector fields. Okay. Okay, so I have other properties, and then I will be able to give examples. Yeah, just a second. I switch blackboards and then. Their friend. Yes.
This last sentence is
Yeah.
What kind of Lie group? The last sentence on the last word.
What do you mean?
It's automorphism of X is a something Lie group, right?
It's a real Lie group. Real Lie group. Yeah. And if you have that V is, if V is some vector fields which is an infinitesimal generator there, then IV cannot be also in the Lie algebra, because otherwise you have a complex one-parameter subgroup, and you have an image of C in your manifold, right? So, okay. Okay. Okay, though also, so this is a very important thing. So if X is compact, then you have this so-called Brody lemma, which tells you that this property 4 up there, okay, is indeed a characterization of compact hyperbolic spaces. Okay, so if you do have a non-constant holomorphic curve, then for sure you are not hyperbolic. Okay, but this Brody lemma permits you, out of the datum of not being hyperbolic, to build a non-constant holomorphic curve. Okay. So if X is compact, then X is hyperbolic if and only if there are no entire curves in X. Okay, so this is Brody. So I'm not going to prove this fact. I'm not going to prove almost anything, indeed. And but it's quite a classical argument in complex. It's an argument of normal families. Okay, something like Ascoli-Arzelà or something like that. Okay. I don't want to. In any case, I will do a little proof in a while, and this kind of argument are more or less the same. So you will see something in action similar to this lemma. Okay? And also, let me also say that if X is compact hyperbolic, then the automorphism group of X is finite. Okay, and because if the automorphism group of a complex space is a complex Lie group. Okay, so then coupled with that, it's you get it must be finite. And last, if X is compact hyperbolic, then you have a better property of regularity for this infinitesimal metric, which is now continuous. Okay, that's a list of properties. And now, the last 20 minutes, I want to give examples and discuss conjectures, and in order to have a better view of what's going on in next lectures. Okay, so examples. So in dimension 1, so if X is a Riemann surface, then by property 3, okay, asking if X is hyperbolic or not is the same as asking if its universal cover is hyperbolic or not. But in dimension 1, you have this magic of uniformization theorem. And so in dimension 1, X is hyperbolic if and only if it is uniformized by the unit disk. Okay? So being uniformized by the unit disk means that X does admit a Riemannian metric with constant curvature, Gaussian curvature equal to -1. Okay? And so if you take this, for instance, in the compact case where the metric is complete, metric with constant curvature -1. So in dimension 1, X is hyperbolic if and only if it is hyperbolic. Okay, but in the usual sense. Okay. So in particular, if X is compact, then it's if and only if the genus of X is greater than or equal to 2. Okay. Because of course, if the genus is 1 or 0, then the universal cover is P1 or the line or the complex line, and then the universal cover itself gives you a map from non-constant map from C to your manifold. But be careful, because I mean the non-hyperbolicity of P1 and of complex torus are very different in nature. Okay, so the non-hyperbolicity of P1 is algebraic in nature in some sense. Okay, because the map from C is an algebraic map. You just erase one point. Okay. While the non-hyperbolicity of a torus is something very transcendental, because the universal cover is not an algebraic object. Okay, the map is not algebraic. So they're very different in nature. Okay, so maybe here it would be good to spend. So in dimension 1, everything really works very, very well. So you have this trichotomy in dimension 1, the usual one. So you have genus 0, genus 1, and genus greater than or equal to 2. And everything fits well. And so you can characterize being hyperbolic for compact Riemann surfaces from several points of view. Okay, you can talk about curvature, -1. Okay, you can take the canonical bundle of your compact Riemann surfaces and ask it to be ample of positive degree if you want, okay? Or if you want, you take the tangent bundle and you ask it to be negative, okay? So that's an algebraic characterization, which in turns in dimension 1 is the same thing of being of general type, okay, whatever it means, okay? And you also in dimension 1 have an arithmetic characterization whenever the curve is defined over a number field. Okay, it is hyperbolic if and only if you have a finite number of rational points after every finite extension of this defined field. Okay, that's not easy, I think. Okay. Yeah, that's Faltings. So, okay. Okay, here. Okay, so that's for dimension 1.
All the subvarieties are hyperbolic, is the variety hyperbolic? You say that a subvariety or hyperbolic variety is hyperbolic, but the contrary, if all the subvarieties, proper subvarieties, are hyperbolic, yeah.
Never thought about this question.
Well, if you take a toggle without any Nabila surface.
Yeah, that's a good answer. Yeah, he was my student. Thank you. Yeah. Yeah, you take a simple abelian surface, and you don't have You don't have rational curves. You don't have elliptic curves because it's simple, but it's not hyperbolic. Yeah.
Then I'm projective.
Projective.
Yeah.
Simple abelian surface.
What is that? There are no elliptic curves.
There are no elliptic curves, nor rational curves, and yeah. Okay. So this is the next series of examples. Maybe the most classical one. Okay, for hyperbolic manifold in all dimensions. So now take X compact, and suppose there exists some étal cover omega on X such that omega is holomorphic to a bounded domain in Cn. Okay? So then X is hyperbolic. This is just Liouville theorem. So in this case, you just have to check the absence of entire curves. If you do have an entire curve in X, you can lift it up to omega. Okay, because C is simply connected, so you lift it up here, and since this is bounded, so this lift must be constant, and so the starting curve must be constant. Okay, so these are examples of hyperbolic, compact hyperbolic manifolds in all dimensions, and so for a very long time there was more or less the only examples. So of course, in this case, you must have infinite fundamental group. Okay, so this is not compact. Okay, so there was so much the only examples that at some point Kobayashi asked if necessarily a compact hyperbolic manifold must have infinite fundamental group. Okay, so the answer is no. And remark also that such a manifold, even if in principle I just asked to be a compact complex manifold, so this is indeed projective and also canonically polarized. So the canonical bundle of such an X is always ample. Okay. You can show this by using this Bergman metric on omega, which is some metric which is invariantly constructed on omega, and which descend on X has a metric on the canonical bundle whose curvature is positive. Okay, I don't want to say a little more than this about this, but okay. Okay. So in this case, in particular, X has ample canonical bundle, and it is then what you say of general type. Okay. You can show a little bit more. It was recently shown by Sébastien Buxom and myself. It's very easy indeed to show that also every submanifold of X is of general type. Okay, so that's what Francesco was asking. So in this case, indeed, every submanifold is of general type. So you see that hyperbolicity, it's an hereditary property, okay? When you pass to submanifold, you keep this notion. While being of general type is not. Okay, you can have manifold of general type with ample canonical bundle, which does contain rational curves or something which is not of general type inside. So being of general type is not stable under passing to submanifold, why being hyperbolic is. Okay, and in this case, you also have stability for being of general type when you pass to submanifold in this kind of manifold X, covered by a bounded domain. Okay. So what about curvature? So now you take some x omega to be an Hermitian manifold. So when you have an Hermitian manifold, you can do the Chern theory. It's the analogous of Levi-Civita theory in the Hermitian case. You can construct a unique connection which is compatible with your data. Out of this connection, you take the square, you consider the curvature, okay? And out of this, you can construct the analogous of what is called the Riemannian sectional curvature, okay? Which is the holomorphic sectional curvature. Okay, maybe I'll give some details later of tomorrow. Okay, but if you have an Hermitian metric whose curvature is bounded above by a negative constant, okay, this is in the compact case it just suffices to take less than 0. Okay, but if it's not compact, you have to stay below 0 in a safe way. And so in this case, also X is hyperbolic. Okay, so I wanted to give a proof of this. I don't know if I have time, but for sure I will give tomorrow because it's linked with then with jet differentials and so on. So I will give a proof of this. This is a toy case for much more sophisticated properties. So what I wanted to say is that, okay, so is this a new class of example with respect to, okay, so which are manifold with negative holomorphic sectional curvature, okay? So I looked a little bit literature, and it's very difficult to find examples. So more or less, the only examples I was able to find since 1 year ago, till 1 year ago, sorry, was bounded symmetric domains. So not only bounded domains, but also symmetric. Okay, for these domains, the Bergman metric does have negative holomorphic sectional curvature, and then also for compact quotients. Okay. And in general, if the domain is not bounded, sorry. Étal. You want to be an isometry. Okay. And but then it's an old paper by Kobayashi. He computed the holomorphic sectional curvature for a general bounded domain, not necessarily symmetric. And all you can do is bound from above the curvature by the number 2, which is positive. Okay. So, but are there other examples? So in principle, this situation here seems to be, in some sense, more general. Okay, if you do have only these examples here. But then there was a very, very nice and interesting paper by Jean-Paul Mosen 2 years ago, where he constructed a lot of simply connected example, compact simply connected example of manifold of negative holomorphic sectional. So examples here, simply connected example. Were constructed by Paul Mosen. So these are of this type. You take some y of dimension d into some projective manifold x of dimension n, okay, with an ample line bundle A on x, okay, and y is a complete intersection, say h1, h n minus d plus 1. How many do you need? Yeah, I guess it's correct. I don't know. Minus d? Okay, minus d. Okay. For 1, right. Yeah. Okay, and so each hj is in the linear system of some high power of a. Okay, and so the example tells you that if n is greater or equal than 3d and k is very large, then you can construct like this projective manifolds with negative holomorphic sectional curvature. Okay, and these are complete intersections. So if you start from Pn, for instance, or if you start by something which is simply connected by hyperplane Lash theorem, you get simply connectedness on this example. And if you go deeper here, you can also have holomorphic bisectional curvature to be negative, which is something stronger, okay, which correspond more or less to ampleness of the cotangent bundle. Okay, so that's very, very interesting. So there are examples which are different from those where you can study like this. And I have to say that also for this class of manifolds, you do have this property of being of general type also when passing to submanifolds. Okay? So suppose you have some, you need Kähler. Okay? So suppose you have x omega to be a Kähler manifold with negative, compact Kähler manifold with negative holomorphic sectional curvature. Okay? So there is this fits property in Hermitian geometry. It's a general principle. When you have a metric and you look at the curvature, when you pass to sub-thing and you look at the restriction of the metric, the curvature of the sub-thing is less than the curvature of the whole thing. Okay? The curvature is always decreasing when you go down. Okay? So you see that if you have a manifold with negative holomorphic sectional curvature, if you look at to a smooth submanifold, and you restrict the metric, it will also have a negative holomorphic sectional curvature. So there was a breakthrough by Wu and Yao 3 years ago, more or less, which tells you that a manifold with this property has ample canonical bundle. Okay? So once you have this, you look at smooth submanifold, and by this decreasing property, they will also have ample canonical bundle. But now the point is, what about singular submanifolds? Okay, so that's much more difficult. And it was achieved last summer by Henri Guénancia, who was able to show that under this hypothesis, indeed, you always have that even singular submanifold, subvarieties, are of general type. Okay, so in all of these big classes of examples, okay, you have this property that being of general type is stable under passing to submanifolds and subvarieties also, okay? And this is really the content of one very important conjecture in the subject, okay? So let me finish with a couple of conjectures, and then I will do more proofs tomorrow. Conjecture it's a conjecture by Long from '86, And it states the following. So you take X to be projective, or maybe compact Kähler. I don't know. And so by a sort of universal Gaga principle, hyperbolicity is an analytic property, right? But in the projective case, you expect it to be also algebraically characterizable in some sense, okay? And so maybe the most naive idea is to say, okay, in dimension 1, being hyperbolic is equivalent to being of general type. And being of general type is not stable when you pass to subvarieties. Being hyperbolic is. Okay, so let's impose it, okay? So that's the conjecture. So I don't know if anyone has defined being of general type the first week. Should I do this? Should I define general type? Okay. If I remember. Okay, so being of general type is something which concerns the positivity of the canonical bundle. Okay, so you have your X, so general type. You take X, out of X you construct the canonical bundle, which is the determinant of the cotangent bundle. So it's a line bundle of holomorphic n forms, top degree forms, okay? And then you look at this sequence of number, so the plurigener of X, which is the dimension of the space of section of tensor power, global holomorphic section of tensor power of Kx. Okay, and it is, one of several definitions of being of general type is asking that the growth of this integer number is big as possible. Okay, you require it growing like a constant time n, m to the dimension of x. Which is the same of saying that the ring of this section have transcendence degree n plus 1, which is the same of saying that if you look at the Kodaira maps associated to these complete linear systems, at some point this gives a birational map. Okay, you have several definitions. But just keep in mind, if you have seen ample line bundle, so if Kx is ample, then it is X is of general type. That's a special case, okay? And so hyperbolicity should be characterized as being of general type for all subvarieties. Now, if a subvariety is, oh, sorry, what's up? It's 3 minutes. If 3 minutes late, okay. I thought it was like 10 minutes, it's okay. I didn't want to talk about general type. They asked me, okay, so. And, okay, now I forgot what I wanted to say. I stop here.